chemical equation indicates? It indicates the energy changes and also physical state of the reactants and products. In addition to energy changes, the physical state, is it solid, liquid or gas? It also may be a solid, liquid, gas. It is also a solid, liquid, gas, solid, liquid, gas. And number of coefficients, here 1 mole, here 1 mole, 1 mole, 1 mole. During this chemical process, there is a change in their heat, internal energy or enthalpy. That change is denoted by delta H. That is either maybe a positive value or maybe a negative value. Okay. Now here delta H positive or negative depending upon the type of chemical reaction, because amount of heat is absorbed by the reactants. It is amount of heat absorbed by the system. Heat is absorbed, delta H is equals to positive. Amount of heat is liberated from the system, that is a negative value. Now here these are the reactants. Reactants enthalpy is HR. These are the products, enthalpy is HP. We know change in enthalpy delta H is equals to HP minus HR. This is. If the enthalpy of the products is greater than the enthalpy of reactants, substitute here, will get a positive value. If here the HP is less than HR, then delta H is equals to HP minus HR. This value is equals to more, negative value is more, minus, positive. That's why amount of heat is some cases liberated, some cases absorbed. So based on this, thermochemical equation is the one chemical equation in which amount of heat is evolved or absorbed. In addition to amount of heat is evolved, absorbed, in addition to that, your physical state of the reactants and products mentioned, and also coefficients of the reactants and products mentioned. Such reactions are called thermochemical equations. Yesterday just explained. Based on this, here two important reactions are there. One is exothermic. Exo means out, Greek language. Thermo means heat. Heat out. Means your exothermic reaction is the type of thermochemical reaction from which amount of heat is evolved. Means from system to the surrounding, amount of heat is evolved. Now it is a system. Now it is a system. That system contains here, it is a system. From system to the surrounding, your amount of heat is Q or H is liberated. Liberated means out, that is exothermic process. Okay. Now here from system means your system contains reactants A plus B, amount of heat is liberated. Such chemical reactions are called exothermic reactions. For example, here, your A plus B gives C plus D. Liberated is nothing but from system to the surrounding. That heat on product side we can write Q kilojoules. or kilocalories per mole, because the heat is expressed in terms of joules, calories, ergs, kilojoules. Now, this is also we can write A plus B gives C plus D, comma, that change delta H is equals to minus Q kilojoules. Wherever in an examination, while doing some problems, if they'll give like this, it is a gaseous reaction, it is a gas, it is a gas, and it is also a gas. Number of moles 1, 1, 1, 1. Physical state mentioned, number of moles of the reactants and products mentioned, and delta H also mentioned. That's why it is thermochemical reaction. In this process, amount of heat is evolved. That's why it is an example of exothermic reaction. Exothermic reaction is a type of thermochemical equation in which amount of heat is evolved, liberated. After liberating some amount of heat, the system becomes cool in nature. Clear? After this, your endothermic reaction. Endo means inside. Thermic means heat. Just like this exothermic reaction, your endothermic reaction is a type of thermochemical equation in which amount of heat is absorbed by the system. Now, it is a system containing reactants. Your system, that system absorbs some amount of heat from surroundings. The system becomes hot in nature. Now, here the A plus B is a gas, may be converted into C plus D. Now, it is also a gas, it is also a gas. Here we can write up minus Q kilojoules. This is the general representation of endothermic reaction. Also, we can write A plus B gives C plus D, comma, delta H is equals to plus Q kilojoules. Amount of heat is absorbed by the system from surroundings. So, are the exothermic and endothermic reactions. Based on this exothermic and endothermic, some important features of thermochemical equation. Here are some important features of thermochemical are the features of thermochemical equations. We know thermochemical equation is A plus B gives C plus D, comma, delta H is equals to plus or minus Q kilojoules per mole. It is maybe a solid, gas. Here it is a gas, it is a gas. Now here 1 mole, here 1 mole, here 1 mole, here 1 mole. Your first feature is thermochemical equation indicate the physical state of the each and every one participant present in a reaction. Second point is here number of coefficients. Number of coefficients, nothing but number of moles. Then here heat is liberated. It indicates heat is liberated or absorbed. Also, in this chemical reaction, chemical reactions are multiplied or divided with respective integers. The value of delta H is also multiply are divided with respect to integer. If the reaction is reversed, the magnitude of delta H is the same, but sign of delta H is changed, that is reversed. These are the some important features of thermochemical equations. Now I will write an important simple example for this. Very simple example. By using all this, now original I will write a very simple example. It is a graphite. Carbon is a graphite state, allotropic form. It is a solid. Reacts with the oxygen gas, it gives carbon dioxide, also a gas. Now delta H is equals to minus 393 kilojoules per mole. This value is experimentally determined by bomb calorimeter. No need to remember. While doing problems, they'll give the value. Don't bother about it. Just remember, if the delta H value is negative, is it exothermic or endothermic? That's all. Delta H value is negative, that is exothermic reaction. It is a thermochemical reaction because reactants, physical state, solid, gas, gas mentioned, and number of moles, 1 mole, 1 mole, 1 mole mentioned. Then here the enthalpy, heat liberated or observed, also mentioned. That's why physical state, number of coefficients, heat is liberated or observed, and this is very, very important. If the reaction is multiplied, divided with respect to integer, I want 2 moles, then I'll multiply the equation. 2 into C plus 2 O2 gives 2 CO2. Then here the delta H also multiply with 2, that is minus 2 into 393.5 kilojoules. Value also multiply. If you want to divide, C by 2 plus O2 by 2 gives here the 1 by 2 CO2, then value also divided. This is equals to minus 393.5 by 2, wherever or whenever required while doing the problems. That's why if the reaction is multiplied with respect to integer like 2, 3, 4, 5 or divided certain respective numbers, this value also multiply. If the reaction is reversed, I'll reverse this reaction, that is products can be converted into reactants, reactants can be converted into products, reversed. Gas, CO2 gas gives C solid plus O2 oxygen. In this case it is minus, value remains constant but sign change, reverse, positive 393.5 kilojoules. These are very, very important. With the help of all the, just I'll introduce all definitions. I'll finish thermochemistry, all definitions with a single statement, all single statements, different points based on these simple features of thermochemical equations. Thermochemical equation features and exothermic and endothermic reaction by using a simple reaction introduced to you. Based on this, I'll introduce some important reactions with the help of thermochemical equations. I'll introduce one important concept, that is enthalpy of reaction. The enthalpy of a reaction is denoted by symbol delta H, or it is. Sorry, here enthalpy means change. Reaction means chemical reaction, chemical equation. So here the enthalpy of reaction is the change in enthalpy occurs when all the reactants present in a chemical reaction have been completely reacted and converted into products. That is called enthalpy of reaction. The same enthalpy of reaction is calculated under standard conditions. That is called standard enthalpy of reaction. That is denoted by delta H naught R. This is the standard enthalpy of reaction. So the enthalpy of reaction is the change in enthalpy occurs when all the participants, reactants present in a reaction have been completely reacted and converted into products. During the conversion, there is a certain small change. For example, here I will take two examples, different examples. Here the CaCO3 calcium carbonate is a solid. Then here on heating, it gives CaO plus CO2. It is a gas. It is a solid. Now it is a solid. This is a delta H value. No need to remember the value. Just remember positive Q value. Means here the decomposition of calcium carbonate is an endothermic reaction because amount of it is required to decompose these. This is the example for enthalpy of reaction. And also I'll give one more example, that is here H2 plus of O2, it is a gas, it gives here the H2O is a liquid. Now delta H is equals to minus Q kilojoules. The amount of it is liberated. These two are the examples for simple examples for enthalpy of the reaction. That value is calculated under standard conditions, that is at 1 atm pressure and 25 degrees Celsius or 298 kelvins. That is called standard enthalpy of reaction. Now, simple confusion point is here. After enthalpy of reaction, one more important reaction will get it, that is enthalpy of formation. Enthalpy of formation, that is denoted by delta H naught F. Delta HF. That is calculated under standard condition, that is called standard enthalpy. Standard enthalpy of formation, that is delta H naught F. These two are very, very important. Enthalpy of reaction and enthalpy of formation. These two examples are most useful and suitable examples for enthalpy of reaction, but these two examples are not suitable for enthalpy of formation. Standard enthalpy of formation, because your enthalpy of formation is the change in enthalpy that occurs when 1 mole of compound is formed from its constituent elements. But see here this point, here calcium carbonate decomposes, it gives calcium oxide and carbon dioxide. These are compounds. These compounds are not formed by their constituent atoms. These are formed by molecule or a compound. That's why this is the example for enthalpy of reaction. And it is also a example for standard enthalpy or enthalpy of reaction. But among these two, here CaCO3 gives CaO plus CO2. Delta H is equals to plus Q kilojoules is not a suit for this. It is not suit. Because enthalpy of formation is the change in enthalpy occurs when 1 mole of compound is formed. That is 1 mole of H2O is formed. It is a liquid, 1 mole. From its constituent elements, that is hydrogen plus half mole of dioxygen, it is a gas. That's why your formation of water from its constituent elements is a best example for enthalpy of formation. But here it is not example for enthalpy of formation. So here these two are the best examples for enthalpy of the reaction. But these two are not suitable for enthalpy of formation. Because enthalpy of reaction is the common statement for thermochemical reaction. Any substituents, any participant, any substances have completely reacted. These are the participants, completely reacted, converted into products. In such cases, amount of heat is liberated or absorbed. That is called enthalpy of reaction. Whereas enthalpy of formation is the change in enthalpy that occurs when 1 mole of compound is formed. This is the 1 mole of compound is formed. In this compound, hydrogen is there separately and oxygen is there from its constituent elements, not from compounds. That's why it is the example for enthalpy of formation. This is not enthalpy of formation. Clear? Enthalpy of reaction and enthalpy of formation. So the enthalpy of formation is the special case of enthalpy of reaction only. It is one type of reaction present in enthalpy of reaction. So here, for example, 1 mole of NH3, second is ammonia. Manufacture of ammonia by Haber's process, 1 mole of ammonia is formed from its constituent elements like N2 gas plus 3H2 gas. Now here 1 mole is there, that's why 1/2, 3/2. Now here 1 mole of ammonia is formed from its constituent elements. Now this is NH2 and H2. Number of moles, these are the coefficient. This is the example for enthalpy of formation under standard condition, that is minus 46 kilojoules per mole. Amount of it is liberated. That's why it is an exothermic reaction. Clear? Enthalpy of formation and enthalpy of reaction. Just identify the difference, then we'll get the complete clarity about thermochemistry. The remaining all are the simple definitions to solve some problems. Just I'll give a glance about this and I'll start some problems based on this. Okay? So here, this is the standard enthalpy of reaction. This standard enthalpy of reaction generally is calculated by using one important formula, that is summation of number of coefficients of the products and here enthalpy of formation of products minus summation of your number of moles or coefficients of the reactants and enthalpy of standard enthalpy of formation of reactants. This is the formula to calculate the enthalpy of reaction. If they will give the enthalpy, standard enthalpy of formation of products, standard enthalpy of formation of reactants. To calculate this, we can use this formula. The same, if they'll give the bond energies, if the reaction is in gaseous state, in such cases, enthalpy of the reaction is generally calculated summation of bond energies of reactants and summation of bond energies of products. Just identify these two important formulae. Here, enthalpy of formation under standard condition, enthalpy of formation, enthalpy of reaction under standard condition, both are the same. But here the enthalpy of standard enthalpy of reaction, if they'll give the enthalpy of formation for all different types of reactions, we can use product minus reactant enthalpy formations. But if they'll give the bond energies, and here if reactants and products, products are in gas phase, in such cases we can use this reaction. Okay, so while doing problem, these are very, very important to calculate enthalpy of reaction and enthalpy of formation. If they'll give the bond energies, bond enthalpies of reactants and products, here we can use products, but here we can use reactants. Very, very important relations. Already 2 to 3 times given some problems based on these two important formulae. Clear? Here, this enthalpy of reaction delta H naught R depends on one is physical state of reactants and products. Second one is here allotropic forms. Form. Third one is temperature. Fourth one is pressure volume. Fifth one is quantity of the substances. Quantities of the substances. These are the some important factors which influences this delta H naught R enthalpy of reaction. So I'll explaining problems how it depends based on physical state, allotropic forms, temperature, pressure, volume, quantity of the substance. One simple reaction I'll give to you, quantity of the substances, how it depends. Okay. Now here the carbon combines with oxygen, it gives carbon dioxide gas. Now here the delta H is equals to minus 393.5 kilojoules. Once we can observe 12 grams of carbon combines with 44 grams of 32 grams of oxygen, it gives 44 grams of carbon dioxide. Now here minus 393.5 kilojoules amount of it is liberated. This is the standard stoichiometric equation. This is 12 grams is the atomic weight of carbon, 32 is the molecular mass, molecular weight of oxygen, carbon plus oxygen 44 grams of carbon dioxide. This much amount of it is liberated. This is the quantity of carbon, quantity of oxygen, quantity of product formed carbon dioxide. This is because how it influence quantity. For that, I am giving a simple example. 12 grams combines with oxygen, it gives 393.5. For example, only 1.22 grams of carbon only completely reacted. How much amount of it is liberated? For 12 grams of carbon, 393.5 kilojoules liberated. 1.2 grams, how much? So that's why this value delta H naught value R naught delta H naught R value depends on quantity also. For 12 gram this much, for 1.2 how much means cross multiply these, that is 393.5 into 1.22 divided by 12 get cancelled, that is minus 39.35 kilojoules. Amount of heat is liberated value is less. So here the delta H naught value, delta H naught R value depends on quantity like pressure, temperature, volume, allotropic forms. Physical state also depends on delta H naught. Okay. So based on this delta H naught R, that is enthalpy of reaction and enthalpy of formation, I'll introduce some important basic simple definitions in thermochemistry. Just I'll give the mathematical expressions to get clarity about all different phase transformation values. These mathematical expressions are useful, more useful for problems, to do the problems. Change in enthalpy, change in enthalpy during phase transformation. Phase transformation. Phase means state. State means here a solid, liquid or gas. Change in enthalpy or enthalpy change during phase transformation. In that, first one is delta H naught FUS fusion. We know already delta H naught R and delta H naught F. So standard enthalpy of reaction, standard enthalpy of formation. Based on this, first one is fusion. So the standard enthalpy of fusion is the change in enthalpy occurs when your solid is converted into a liquid. There is some change, that change is a enthalpy of FUS fusion. That's all, definition. So this is for objective, no need to explain definition, but based on this I'll create some problems. Enthalpy of fusion, meaning solid is converted into liquid. While converting solids to liquid, there is some change in their enthalpies, that is called a fusion. Clear? Then next one is standard enthalpy of VAP. What is that VAP? Vapor pressure. Standard enthalpy of vapor pressure, vapor. That is here a liquid is converted into a gas. Now here the delta H naught vapor this is. Now third one is standard enthalpy of SUB, sublimation. Direct solid is converted into a gas. Now that is delta H naught SUB, sublimation. Once we can observe this, by adding all this, liquid cancel. Here the solid and solid to gas like. Here the solid is directly converted into gas by adding all this. So the direct conversion of solid to gas is called a sublimation. That's why enthalpy of sublimation is the generally sum of the enthalpy of fusion plus enthalpy of vaporization. This is a very important relation. So instead of giving direct enthalpy of sublimation, if they'll give enthalpy of fusion and enthalpy of vaporization, better use this formula to get enthalpy of sublimation. For example, your iodine is a solid converted into a iodine vapors, gas. Naphthalene balls converted into a naphthalene vapors. Here, vapors. Your H2O liquid is converted into H2O gas. Here, fusion. Your H2O solid means ice is converted into H2O liquid are the examples for this. Just only remember these simple statements and the mathematical expressions. Here these values they'll create while doing problems, either plus or minus their values, respective values they'll create. Enthalpy of fusion is nothing but is a process in which solid is converted into liquid. In such process, there is something change in their heat, that is change in enthalpy during phase transformation, one state to the another state. Okay. Then after this, enthalpy of sublimation, enthalpy of vaporization, enthalpy of fusion. Most important, another important term is enthalpy of solution. So the enthalpy of solution is the change in enthalpy occurs when 1 mole of ionic crystal is dissolved in an aqueous solution. There is something change in their enthalpies. For example, here AB is a ionic solid is dissolved in aqueous water H2O. Then it gives A plus aqueous plus B minus aqueous. This is, that is enthalpy of a solution, delta H naught SOL. But this AB solid is converted into A plus gaseous ions plus B minus gaseous ions, respective oppositely charged ions. Some amount of energy required, the required amount of energy is called a lattice enthalpy. After converting ionic solid to a gaseous ions by using some amount of energy, these ions are dissolved in water H2O, that is in aqueous. Then it is a enthalpy of hydration, delta H naught HY, hydration this is. So it is a direct step, direct here solution means salt is dissolved in aqueous water, it converted into A plus aqueous and B minus aqueous. Indirectly, this solid AB ionic solid like NaCl, in chemical bonding, Born-Haber cycle is there. There NaCl solid is converted into Na plus gas plus Cl minus gas. That is called a lattice energy of NaCl. That gaseous ions, oppositely charged ions dissolved in water. Then here we will get aqueous Na plus aqueous, and here the Cl minus aqueous. So by using this, common important statement is standard enthalpy of solution is equals to sum of standard enthalpy of lattice energy plus standard enthalpy of hydration. This is a very, very important formula to do some important problems. Okay, phase transformation, solid to the aqueous medium, solid to the gas. Yeah, the solid to the aqueous medium, direct and indirect step, that is by using enthalpy of solution we can calculate. So after this, fifth one is enthalpy of dissociation. Sir, what is the enthalpy of dissociation? The amount of energy required to dissociate into its constituent ions from respective molecule. For example, the hydrogen is a gas, that hydrogen gas is converted into a hydrogen atom, like 2 moles of hydrogen atoms. Either maybe atoms or a free radical converted into a free radical, amount of energy required, that is also called a bond dissociation energy. Now here the hydrogen, there is a bond on covalent bond. To break the covalent bond, some amount of energy required to convert into its respective atoms. That is called a bond dissociation energy. But here there is a lot of variation between bond dissociation energy and bond enthalpy. I'll explain. bond dissociation and bond enthalpies. So here delta H naught bond dissociation energy and bond dissociation, or simply a dissociation we can use. And another one is bond enthalpy. Bond enthalpy this is. So the bond enthalpy and bond dissociation is slightly varied and differ, both are not the same. For example, here the CH4 is a gas is converted into carbon plus 4 hydrogen atoms. See here, around carbon, how many bonds are there here? 4 covalent bonds are there, carbon and hydrogen. To break here carbon to the hydrogen, carbon to hydrogen, carbon to hydrogen, carbon to hydrogen, some amount of energy required, that is called a dissociation. But whereas it is a polyatomic, CH4 is a polyatomic because it contains 4 covalent bonds are there, carbon, hydrogen, carbon, hydrogen like. Now here first to break here a carbon hydrogen, some amount of energy required, and again to break here a carbon hydrogen, some amount of energy, and again carbon and hydrogen, some amount of energy required. First here to convert here to here, here the CH3 bond H, some amount of energy required, that is called bond energy 1. This is called a simply dissociation because only one carbon and hydrogen bond is cleaved here. Then again here the CH2 bond H again decomposes, dissociated, gives CH2 plus H. Now this is called, again it is a dissociation. Now here the CH bond here H gives CH bond H. This is also a bond dissociation. Now here the CH gives here the C plus H. Now here this is also a dissociation energy. So here the CH4 converted into carbon and 4 hydrogen atoms. How many steps required here? 4 steps required here. So here by using this, bond dissociation enthalpy is the average dissociation energies of each and every one step. Here in first step plus bond dissociation energy of in second step, third and fourth step divided by 4. So the dissociation is the amount of energy to break even single covalent bond. That's all. Clear? Whereas for a polyatomic molecule, molecules, your bond enthalpy is the average bond dissociation energy is present in a molecule. So the carbon and hydrogen to break a bond, some amount of energy required, that is called dissociation. But here, around carbon to break all 4 covalent bonds, the amount of energy required, that is called a bond dissociation or bond enthalpy. So finally, bond dissociation means only to break one covalent bond. To break all 4 covalent or any covalent bonds present in a molecule, we want bond enthalpy, that is called a bond dissociation. Bond enthalpy is the average of bond dissociation enthalpies present in each and every one single step. Here divided by 4 because 4 covalent bonds are ready to cleave and 4 dissociation values are there. That's why here step 1, 2, 3, 4 divided by 4. If it is 3 is there, for example, NH3 is there. So around nitrogen only 3 hydrogen bonds are there, nitrogen, hydrogen. That's why divided by 3 we can take. Because nitrogen, hydrogen, nitrogen, hydrogen, nitrogen, hydrogen. To break only one bond, nitrogen, hydrogen, that is called a dissociation, that's all. But to break all bonds, as NH3 gives N plus 3H, we want, that is called a bond energy or bond enthalpy. For this, continuously 3 to 4 years given in previous examination, I'll give a simple question based on this directly right now. If you have see the material, so the previous year's NEET questions. Question number 7, bond dissociation enthalpies of hydrogen, Cl2 and HCl given. Then enthalpy of formation of HCl is one model given. Then next one is question number 11 is, that is NEET 2009. From the following bond energies, hydrogen bond energy given, carbon double bond energy given, carbon single bond energy given, carbon hydrogen given. Then here enthalpy for the reaction will be given here. Enthalpy of the reaction, how to calculate. So based on this, here based on this bond enthalpies, some important and also question number 6 also given. Given that bond energies of hydrogen, chlorine, respectively, bond enthalpy of formation of HCl is given. I'll solve these 3 important models based on these bond energies, bond dissociation, and bond enthalpies. See, question number 6. Given that bond energies of H2, Cl2 given, and enthalpy of formation for HCl is given, but there is incorrect statement, then calculate bond energies of HCl given. For this, your bond energies of hydrogen given, and here the Cl bond Cl given. To break the bond, some amount of energy given, required given, and also delta H naught F for HCl given, formation of HCl given value. This is the question number 6. Then calculate the bond energy of HCl. In question number 6, this statement is not given, just note down this. Then here calculate the bond energy of hydrochloric acid. Already given to you. Here enthalpy of formation or enthalpy of reaction under standard condition. If the reactants and products are in a gaseous state, there is an important concept, that is a summation of bond energies of reactants minus summation of bond energies of products. Also are the summation of bond energies of reactants, bond energies of product. One statement already given, on formula created for you. Now by using this, here most important concept is here. Your bond energy of HCl we want. Now here the formation of HCl given. Formation means this is H bond Cl. From its constituent elements means hydrogen plus Cl bond Cl. Now this is H2 plus Cl2 gives 2HCl. This is. Your statement is only for HCl given, but here 2 HCl given. Finally, divide by 2 will get the correct answer. Now it is a gas, it is a gas, it is also a gas. All the reactors and products are in a gaseous state. When they are in gaseous state, we can use standard enthalpy of reaction or the formation, this formula. To break this hydrogen and hydrogen, energy value given, that energy is 430 kilojoules. And also to break Cl bond Cl, and the value is given here 240 kilojoules given. And here to form means, while forming this HCl, this value is minus 90 kilojoules given. We want H bond Cl, but here 2 given. In answer, we will get the 2, that is divided by 2, we will get the answer. To break this H and Cl, how much amount of energy required? So, according to this concept, these are the reactant values, this is the product value, and this is the delta H naught F given, that is minus 90 is equals to, formula I will write, delta H naught F is equals to summation of bond energies of reactants minus summation of bond energies of products. These are the reactants. Right, reactants? You are the 430 plus 240 reactant sum. Minus product under HCl. We want this. That is bond energy of products. But this value is given 90. Minus 90. Now here the bond energy of 2 HCl will get it here, not 1 HCl, because in this equation balanced reaction 2 HCl is there. That's why here the 430 plus 240, this minus, that side here the plus 90. So take this value, how much will get it? Here 670 plus 90, 850, this is 850 kilojoules. That is for 2 HCl. So are the 2 into HCl to break the bond here the 850 kilojoules amount of energy required. But asked question is bond energy of HCl only 1, but here 2 are there. For 1 how much? That is 850 divided by 2, that is 425 kilojoules. Amount of it is required to break 1 hydrogen chlorine bonds. Clear? So here the based on this phase transformation, bond energies, bond dissociation, fusion, like sublimation, hydration, solution, so many problems are there. Let's solve it. Question number 6 completed. Then see the question number 7 also. Bond dissociation enthalpies of H2, Cl2, HCl are given. Then enthalpy of formation of HCl, same here. Question number 7, your H2, Cl2 and HCl bond energies given, that is 434, your 242 and 431 given. Then calculate delta H naught Ef. Formula is there. Summation of bond energies are the dissociation energy of reactants minus summation of bond energies of products. Here we will get the 2 moles, will get it, divide by 2, will get the answer. Question number 7. And also question number 11. Same. Data given. Chemical reaction given, one important chemical reaction given. Here C double bond C, one chemical reaction is question number 11 is better do it homework for you, otherwise tomorrow I will complete. Better tomorrow bring this material, keep on side, and I'll solve all models with the help of spontaneity. Question number 11 is, say double bond, say like H given. Now here the H bond, H gives alkene is converted into a alkane. This is alkene. This is ethane. This is alkane. This is ethane. So I'll converting alkenes to alkane. Carbon hydrogen, carbon carbon double bond, hydrogen hydrogen, carbon carbon single bond, all bond energies given. Then calculate bond enthalpy of formation. Okay, tomorrow homework, and tomorrow maximum I'll cover all these models. Better bring this material. Okay, thank you.